In this section, we'll look at constructing confidence intervals for both the population mean and the population proportion from the binomial distribution. For the population mean, we'll discuss methods for both large samples and small samples. Let's look at the first example. A fishing company wants to know the average weight of the salmon they catch. In a random sample of 200 salmon, the average weight is 9.3 pounds with a standard deviation of 0.75 pounds. Construct a 95% confidence interval for the mean weight of salmon caught by this company. So this is a large sample. Since the sample size is 200, and that sample size is greater than or equal to 30. Any sample size greater than or equal to 30 will mean you're dealing with a large sample and you can use the normal distribution, which means you can use a z-score. In this case, X bar, the sample mean, is 9.3 pounds. This is the mean that came from the sample of 200 salmon. The sample standard deviation is 0.75 pounds. Again, this is the sample standard deviation because it came from the sample of 200 salmon. This would get done the exact same way if you had had the population standard deviation, which is less likely but possible. Since we're looking for a 95% confidence interval, we are looking for a z-score such that 95% of the area is between z and negative z. This is something that you can figure out, but you're also able to use the normal distribution table, which has some common levels of confidence and their critical values associated with them. This is found on the positive side in the lower left-hand corner. In this case, we can see that 0.95 or 95% has a corresponding value of 1.96. This is the z-score such that 95% lies between the positive z and the negative z. So this z-score is 1.96 and negative 1.96. About 95% of the area lies between those two z-scores. So the z we'll be using for 95 is 1.96. Now we're looking to calculate the error. So our error is calculated by multiplying the z-score by s, or sigma if you have it, over the square root of n. The z-score is 1.96 times 0.75 over the square root of 200. This gives us an error of about 0.1039 pounds. What this error means is that we believe from our sample that our sample mean 9.3 is within 0.1039 pounds of mu, the population mean weight of all the salmon. So to construct our 95% confidence interval, we need to find a lower number and a higher number that we believe the true mean lies between. To do this, all we need to do is take the sample mean and subtract the error, then take the sample mean and add the error. This gives us an interval of 9.1961 to 9.4039. Again, what this means is that we believe that our true mean weight of salmon lies somewhere between these two numbers. So we can say that we are about 95% confident that the population mean weight of salmon caught by this company is between 9.1961 pounds and 9.4039 pounds. Let's look at a small sample estimation. In a random sample of 15 Major League Baseball games, an average of 108 baseballs was used with a standard deviation of 6.7. Construct a 90% confidence interval for the mean weight for the mean number of baseballs used in a Major League Baseball game. So this is a small sample, as in this case, n is 15, which is less than 30. Anytime a sample is less than 30, then we consider it a small sample. In this case, X bar is 108, the average of 108 baseballs used from this sample of 15 games, with a standard deviation of 6.7. Now, in this case, it's very important that we recognize that 6.7 is S. Since 6.7 is S and we have a small sample, then this means that we need to use the t distribution. If we had sigma here, which is less likely, but again, possible, then we could actually have used the standard normal distribution and proceeded the same way we did in the previous problem. Since we have a small sample and we have the sample standard deviation, which again is the most common scenario, then we're going to have to use the t distribution, which comes from a different table. For the t distribution, we first need to find what we call the degrees of freedom, normally just abbreviated df. Degrees of freedom is simply n minus 1. So in this case, degrees of freedom is 14. We also need to find the area in the tails here. What this means is similar to the previous problem. In this case, we're looking for two values such that 90% lies between. Now, this is drawn similar to a normal distribution because the t distribution is similar. But however, we are looking for the area in just one of the tails here. Since 90% is between these two values, that means there's 10% total between the two unshaded values. Since the t distribution, like the normal distribution, is symmetric, then we can say that there's a remaining 10% or 0.10 that is split evenly between these two tails, so each tail contains 5% or 0.05. This value on the table that you will use is called alpha. So when we look up the values on the table, we were looking under degrees of freedom 14 and an alpha of 0.05. If we look at the t distribution, we look for 0.05 and we look for degrees of freedom 14. We can see here that this gives us a value of 1.761. This will be used the same way as the z-score was used in the previous problem. Just in this case, since it was a small sample and we only had the sample standard deviation, we're using a t-score. So our t-score is 1.761. The rest of the problem is calculated very similarly to how the previous one was calculated. The error formula is almost the same, except in this case, instead of using z, we're using t. And again, we're still using s over the square root of n. If we had, again, the population standard deviation, we could have actually used z here, but since it was the sample standard deviation, we had to use t. So we have 1.761 times s, 6.7, over the square root of n, so the square root of 15. This gives us an error of about 3.0464 balls. Because remember, what we're trying to find is the true average number of baseballs used. So we think that the true number is within 3.0464 balls of 108. So to construct our 90% confidence interval, we will do the same thing we did in the previous problem, which is to take the sample mean, subtract the standard deviation, and then take the sample mean and add the standard deviation. So we get an interval of 104.9536 to 111.0464. So since this is an interval for the number of baseballs used in a game, what we can say here is that we are about 90% confident that the population average, or mean, number of baseballs used in a game is between 105 and 111. It's okay to round here since we know we're dealing with the number of baseballs. For the last problem, we'll estimate a population proportion from the binomial distribution. This is the p-value that you used in the formula to calculate binomial probabilities. So the p referring to the probability of success. So in a random sample of 500 people, 235 say that they believe in extraterrestrial life. Construct a 99% confidence interval for the population proportion number of people who believe in extraterrestrial life. So we can set this up similarly to how we would any other binomial problem. In this case, we consider success the person believes in extraterrestrial life. This means failure is the person does not believe in extraterrestrial life. Now, in this case, we're not given the value of p, the probability of success. So we need to look at the sample. In the sample, 235 said that they do believe in extraterrestrial life. This means we got 235 successes out of a total of 500 people. This makes R 235. Remember that R is always the number of successes. In this case, N is 500. We can now calculate what we call p hat. P hat is the sample proportion, or the sample probability of success. We calculate this by dividing the number of successes over n. So we have 235 divided by 500. This gives us a sample proportion of 0.47. Now we need to calculate Q hat, which is calculated the same way that Q is calculated. Q hat will just be 1 minus P hat. So we have 1 minus 0.47, which is 0.53. The next thing we have to do is verify that the sample is large enough. We need to verify that the sample is large enough to use the normal distribution. We do this by calculating n times p hat and n times q hat. As long as both values are greater than 5, then this sample is large enough to use the normal distribution. So n times p hat, 500 times 0.47, is 235, which is definitely greater than 5. And n times q hat is 500 times 0.53, which will definitely also be greater than q hat, since then n times p hat, since q hat is larger than p hat. And here we get 265. This tells us that we are dealing with a large sample, so we can use the normal distribution. So we need to calculate the error. The error is calculated by using the z-score for 99% confidence interval times the square root of p hat times q hat divided by n. So before we can calculate this, we need the critical value for a 99% confidence interval. Again, this we can get directly off of the normal distribution table. We can see here that for 99%, the critical value is 2.58. So we have 2.58 times the square root of 0.47 times 0.53 divided by n, which is 500. After substituting this into your calculator, you get that the error is approximately 0.0576. Again, this is the margin of error for the population proportion. Since the proportion, the sample proportion was about 0.47 or 47%, then the error is around 5.76%. So to calculate the 99% confidence interval, we'll do this the same way we did for the mean. This is the 99% confidence interval for P, which we'll use P hat to calculate. So to calculate the confidence interval, we'll do this similar to how we did the mean, except again, we'll use P hat. So we have a similar looking confidence interval here, where we have 0.47 minus 0.0576 and 0.47 plus 0.0576. This gives us an interval of 0.4124 and 0.5276. So the way we can interpret this is that we can say we're about 99% confident that the population proportion of people who believe in extraterrestrial life is between 0.4124 and 0.5276, or if you want, 41.24% and 52.76%.